Welcome to the chapter on amines. Now, amines include, a lot of biologically active compounds, and such as cocaine, nicotine, which is found in tobacco, morphine, and these are natural products, and they're biologically active, and these are also called alkaloids. And you can look at their structures. They're pretty complex. They have stereocenters. Um, Most drugs of addiction are classified as alkaloids. You can see a lot of your vitamins, like vitamin B6 is a biological active amine, histamine, your amino acid, tryptophan, epinephrine. So if you go into drug design, more than likely your drug molecule will have a nitrogen, some kind of amine functional group in that structure. So in basic organic chemistry, we really don't talk a lot about amines. So this is your only chapter really on amines. We'll talk about the physical properties and how these are the organic bases. And we'll talk about that a little bit, but when I went into drug design and organic synthesis at Eli Lilly, this was probably my sharpest learning curve, and I had to spend a lot of time, like we're talking a couple of years of really learning these reactions, and learning how to isolate and detect these reactions. Because like I said, every one of my molecules every week had some kind of nitrogen amine function. So then the goal here is not for you to learn every reaction there is for amines, but the goal is for you to take home um, that they're the organic bases. So inorganic bases that you're familiar with is like sodium hydroxide or potassium hydroxide. So you think of those hydroxides, and those are in water, okay? But organic bases, you get to put them in organic solvents. And organic solvents are like maybe dichloromethane. You might have stuff like hexanes, or even alcohols, right? Can be organic solvents. And so if you need a base, like triethylamine is a base. And so this is soluble in the organic solvents. So we'll talk about how to rank the basicity of your amines. Other things we'll talk about in this chapter include the physical properties. And so when we think about physical properties, you should think, okay, melting points and boiling points and solubility. And then we're going to talk about how to synthesize amines. And we'll do this through also a classification of amines. And then, so we'll talk about those reactions. And then reactions when amines can be converted to other functional groups. And so that'll be our take-home message. Okay, so I'm looking through your slides. The first thing I'd like to do is classify amines. The first thing you should do is classify amines. They're kind of like alcohols, and if you can classify them, then you can organize your thinking. So nitrogen likes 3 bonds and 2 lone pairs, or 1 lone pair. So 3 bonds, 3 what I call a happy molecule, which is no functional or no formal charge. So no formal charge on nitrogen. It has to have 3 covalent bonds plus 1 lone pair. So anytime you get an extra 4 covalent bonds, then nitrogen gets a plus 1 charge. If nitrogen has 2 covalent bonds plus 2 lone pairs, and it has a -1 charge. You'll never get a +2 charge, and because you got to follow the octet rule for nitrogen. Nitrogen needs 8 electrons. So this is a primary amine. And how would you figure that out? Well, you'd look at your nitrogen and you'd say, how many carbons is this nitrogen bonded to? And it's bonded to 1. This is ammonia. Okay, so this is ammonia. So that is like a methyl. So ammonia is basically no methyl groups. Okay, primary amine, the nitrogen's bonded to at least 1 carbon. If we bond this now, we have 1 hydrogen. Now this is a secondary amine because that nitrogen is bonded to 2 carbons. And this nitrogen is a tertiary amine because this nitrogen is bonded to 1, 2, 3 carbons. And then if you get nitrogen bonded to 4, it gets a plus charge, okay? And this is a quaternary, so you could just say 4, 4. Now, so we always want to classify these amines because that's going to kind of organize our reactions. You can go through the naming. We also have aromatic amines, and so here's an aromatic amine, and this is aniline. So it gives a special name, aniline, and this is an aromatic amine, and that is an electron donating group, so you know that's an orthoparadirector. Now, I'll just show you what kind of how amines are named here. This is substituted, so this is a propyl. And how we did the long change with carbons, we would say like 1,1-dimethyl or something like that. It'd probably be like 3,3-dimethyl. Here you don't have a number, so you would go in, comma in. This would be ethyl, no, propyl. So 3 carbons. Propyl aniline. So instead of having numbers, you would say in dipropyl aniline. So that's kind of different. Okay, there's a lot of heterocyclic amines. You can look those up when you need to know what they are. One that I would expect you to know from doing the alcohol chapters would be the pyridine. I'd expect you to know pyridine because it's an aromatic, and we talked about that's a proton sponge, so it will accept a proton. It does great for deprotonation reactions. We call it the proton sponge, and you make pyridinium. That's a pyridinium. Pyridinium. So by now you know the is an ion, positive charge here. And so this is called a proton sponge. It's organic. You can put it in those organic solvents, and it keeps your nucleophile free with its lone pairs from hydrogen bonding when acid's being generated. Let's look at some hybridization. So, excuse me, hybridization. So if you have, let's say, triethylamine, it's another common one. What is the hybridization of the nitrogen? Well, nitrogen is bonded to 4 things, 1, 2, 3, 4. So that would be sp3. Remember, we can add up our superscripts there. 1 plus 3 is 4. Those are considered 4 things here on nitrogen. That's an sp3. With a lone pair, that's going to be less than 109.5 bond angles. Now, what if you had a conjugated nitrogen? And so, what is this hybridization? Well, do you remember that we said if nitrogen those lone pairs can participate in resonance, they will. Resonance is very strong. And so this would look like this. So that would be a resonance structure. You see that this overall charge is 0 here. The overall charge is 0. You can't put those lone pairs or make a double bond with that carbon because that carbon is sp3. So these carbons are sp3. sp3 carbons cannot take a lone pair or a pi bond because they have no unhybridized p orbitals. So these are, but nitrogen can participate in resonance, so therefore it must be sp2 hybridization. All right, so the next thing we want to look at is the physical properties. Of the amines. You have a nice kind of chart on Blackboard, your PowerPoints, and it compares these molecular weights between 59 and 60. So I will just put this information here and we will see our trend and see if you can look at this data and make some sense of the data. So we have 3 degrees, 8 degrees, 37 degrees Celsius, 48 degrees Celsius, and 97 degrees Celsius. So these are all the same molecular weight between 59 and 60. And what's the lowest boiling point? Tertiary amine. That's why we do the classification. What is this molecule? What's the functional group? This is an ether. What kind of bonding does ether have? Dipole-dipole. And it has a weak dipole-dipole. So it has a weaker dipole-dipole than aldehydes and ketones. So if you had an aldehyde or a ketone, they would have higher boiling points because you have more of a dipole with the carbonyl. But ether has a weak dipole-dipole, so it has 8. But notice the tertiary amine has a weaker, a lower boiling point than the ether. And then we have this one here. Now what's this one classification? A secondary amine. And this one here is a primary amine. And this is a primary alcohol. So this is a different functional group. So why are the alcohols higher? Well, they have hydrogen bonding. And they're stronger hydrogen bonding because the oxygen is more electronegative than the nitrogen. So alcohols are going to have higher boiling points and melting points than amines. Now we have a primary, so this has 2 hydrogen bonding, okay, because it has 2 hydrogens. This one has 1 hydrogen bonding. So there's your difference there and why primary amines have a higher boiling point than secondary. And then tertiary has no hydrogen bond. So it just has dipole-dipole. And you see that it's weak dipole-dipole. So no hydrogen in the tertiary. So it'll have low boiling points. So you want to classify your amines so you can rank your boiling points of similar molecular weight. You will see questions regarding ranking boiling points. Okay, other things. If your nitrogen, your amine has less than 6 carbons, It's going to be water soluble. Water, so like dissolves like, and this is the structure of water. So water will solubilize things that can hydrogen bond. And you'll see that tertiary amine can hydrogen bond with water because it has a lone pair. So you don't have to have a hydrogen in order to be able to hydrogen bond with water, because water has, you just have to have a lone pair. So they are soluble in water. They also smell like rotting fish. So when you work with amines and you work in the lab, you open that cabinet that has your amines and you're like, whew, that smells. All right, so we're also going to look at the basicity of amines. So basicity of amines. And the way we want to look at that, we will compare pKb values. So we've been looking at pKa values. pKa is the acid. So you can see that you have the A there, which stands for acid. And you learn that the lower the pKa value in organic 1, that it is more acidic. So the more willing of that molecule to give up a proton, right? And so we did acid-base reactions such as, let's say we have like a carboxylic acid here, and let's add it with triethylamine. Okay. And then we said, okay, let's decide the carboxylic acid is your acid. So here's your acidic proton, and we said pKa's for acids between 4 and 5. And then we're like, oh, here's an amine with its lone pairs. So this is going to be our base. So the base is going to take the acidic proton and deprotonate the acid. And then over on the product side, we drew our conjugate base, and we drew our conjugate acid. So now the hydrogen goes here, and there's your plus. So this is your conjugate acid, and then we said the pKa for these was about 36. So we said anytime like ammonia or nitrogens, or we just rounded off to 26, 36, because we're comparing these two numbers, and then we say, well, the equilibrium value is going to go to the highest pK value, which is our weakest acid, and that's going to be about, in this case, 31 zeros. So that's a lot of zeros that this is going to go towards the product. So that's how we use our pKa values. I would recommend that you keep doing that. So when you come to these, just keep that with a pKa value, and you can look those up. But when you get a problem where you have to rank the amines in terms of basicity, then it's good to look at the pKb values. And so the pKb values are the bases. So the lower the pKb value, it's the same thing, you're going to have the more basic. And so more willing to accept a proton. And so let's look at your POGL activity 25, Model 1, where it talks about basicity of amines. And then Model 2, we're going to look at amines as bases. So for Model 1, this is POGL 25, titled Amines. We have, this is the basicity of amines. And so you can actually classify these. This first one here, what is it? I like to put my lone pairs in there. AKB 3.01, and it says it's a secondary alkyl. So alkyl means that these are just CH3 groups, This pKb value is 3.24. So remember, the lower the pKb value, the more basic. This, and then we have this one. This is a pKb value of 3.36. This is a pKb value of 4.74. And then this is not alkyl, but this is aromatic. And this is aniline. And that pKb value is 9.4, which is very significantly different, isn't it? Because when we're looking at the numbers between 3 and 9.4, what's 9 minus 3? You're looking at 6 zeros. So you're looking at a difference of that. It's not just 9 and 3. Okay, let's answer question 1A. Consider the amines in Model 1. The first amine on the left is labeled secondary alkyl. For this secondary alkyl amine, how many R groups are attached to the nitrogen? How many did you put? 2? Yes, these R groups are alkyl, so you'd circle those. Identify the remaining amines as alkyl or aryl. All right, well, what's the next one? Did you write alkyl? This one would be alkyl. This one, you wouldn't even say alkyl. You just say ammonia, okay? So that's ammonia. And then this one here is aromatic, which aromatic is aryl, okay? Identify the remaining amines as primary, secondary, or tertiary. So alkyl amine, this one's a secondary. This nitrogen's bonded to 3 carbons, so that's tertiary. This nitrogen's bonded to 1 carbon, that's primary. Ammonia, you just say ammonia. There's no carbons there. And aromatic, you just, I guess you could say primary aromatic because it has the 2 hydrogens. 2. A low pKa value of a compound. What does that mean? If you write a strong acid, there's your A. So a low pKb value would mean a strong base. From the information on Model 1, identify which compound is the strongest base, which compound is the weakest. Okay, so if you have a lower pKb value, that's going to be your strongest. So here we have a 3.0, so this is going to be your strongest. And this gradually increases to 4, 3, 6, 4.74, and then 9. So this one's going to be your weakest. Okay, that's your weakest base because it has the highest pKb value. Using the general classifications of amines, ammonia, primary, secondary, tertiary, rank the strongest to the weakest. So if you want to make a chart where you wrote, you'll put the weakest on top. So weakest base would be aromatic. And then the strongest would be secondary alkyl. And then ammonia would be at the top here under aromatic. And then primary, tertiary, and secondary. So this is kind of like a little blimp there, right? And you can go and you'll have other questions like this in your sapling. Let's go on to Model 2 when we actually look at amines as bases. Model 2, and we're looking at amines as bases. So here we have and you can draw your bonds in. I would recommend drawing your bonds in. And your lone pairs. And then we have this one here. All right, so 5A. A base does what? Donates electrons. A base accepts a proton. In the reaction of methylamine, the top reaction, so this is your methylamine, identify the acid base and conjugate acid base, draw curved arrows to indicate the electron flow. So this is your acidic protons, that would make this your acid, this would make this your base, here's your lone pair, they go and accept the acid, acidic proton, and now it's attached to the nitrogen, so this is your conjugate acid and conjugate base. Now remember, we also go on and we give pKa values. So pKa of water is 15.7, pKa of protonated ammonia, I think we just say it's like 35. Okay, you can actually look at charts, protonated ammonia, let's see. Looking at the chart right now. Amines. So protonated nitrogen. Okay, so for methylamine, we have ethylamine. So actually, I've been given the wrong number. That's why I checked it. All right. pKa values, and you can look up pKa values. Most people like to keep it in pKa values. So this would be about pKa around a 10.6. Okay. So protonated ammonia, NH4, is a pK, and you can write these down too, and you can look them up, pKa of a 9.2. And does that make sense? Well, what's the pKb? What's the pKb value of methylamine? I think they just showed you that, right? Or ethylamine, 3.36. So do you remember pKa plus pKb equals 14? Because that's the pH scale. So let's get out a calculator and do 14 minus 3.36. So pKa would be 10.64. So that makes sense, right? All right. That's how you figure out the pKa value from the pKb value. So where does this go? Between the two of those, actually, that changes everything, doesn't it? It's going to go to the higher number there. So, and what's that? 16, 15 minus 10, you're looking at 5 zeros. So that's your number there. 1, 2, 3, 4, 5. Yeah, times 2, the starting material, actually. All right, so let's keep going. Draw the products, the result. We're actually on 5C. Draw the products, the result when dimethylamine, the bottom reaction, reacts with water. All right, so here we are going to come here and take that. I like to draw them out here. So CH3, CH3, H, and another H here. And then you want to give it a formal charge of positive, plus you get an OH negative. And of course, this is your conjugate acid, and this is dimethylamine. You can look at your chart and see dimethylamine, the pKb of the secondary is 3.01, so pKa value is going to be about 10.6 again here. This is your acid, pKa of 15.7. So technically this reaction arrow should not be that way. Okay, so in the above reaction, the amine reacts with water to form a conjugate acid. The conjugate acid has a positive charge. So do you see that your conjugate acid has a positive charge? Okay. The conjugate acid has a positive charge. In general, what types of effects will help stabilize the conjugate acid? So what they want you to see here is electron donating groups. So your alkyl groups donate electrons. And so electrons have a negative charge, which would help stabilize your positive charge here. Compare the conjugate acid from methylamine. So we're looking at the conjugate acid from methylamine versus the conjugate acid from dimethylamine. This is your dimethylamine. Recall that alkyl groups donate electrons by induction. Which conjugate acid is more stabilized? So the conjugate acid that's going to be more stabilized will be the dimethylamine. Draw polarity arrows on the carbon-nitrogen bond to show this inductive effect. So inductive effect is through the sigma bond, and so your electrons are going this way. So you would have to do this with every bond there, and so you're showing the electrons there. F. Draw the conjugate acid formed when trimethylamine reacts with water. All right, so trimethylamine with water. Trimethyl. Okay, plus water. And then you have your electrons that go here. And you get a positive charge on your nitrogen. And you get the OH, becomes the negative. And I'll just draw that like that. Is this product more or less stabilized by induction to the primary and secondary? And this would be even more so because those electrons would go here and here and here because those are electron donating, so they're going to push those electrons. So you would say it's more stabilized by the induction effect. If the conjugate acid is more stable, that would indicate that the base is more basic. Okay, so if this is more stable, then this is going to be more basic. Is the tertiary amine more basic? And it's still basic, but no, it's not more basic. And so the next question on number 6, and I'm just going to tell you so we don't go through it all, and you don't have to go through it all, but it's because a thing called solvation. And this occurs, so if you read number 6, solvation occurs by hydrogen bonding through the conjugate acid and lone pairs. So what happens when you're measuring acid-base chemistry, this hydrogen bonding in the water when you're measuring your pKb values is solvating that lone pair. And so your measurements are not going to be as basic. Okay, you can go on to 7. Question number 7. You should be able to draw conjugate acids of the following bases. So question number 7, draw the conjugate acid for each of the following base. And so this is most basic. And then you go all the way here is to least basic. So here we have an aliphatic amine. Let's classify it. This is a primary amine, and it's aliphatic. And that conjugate base would be that. Okay. And then the next one is aromatic amine. And so we talked about this. This is a pKb, let's just say a pKb around 3. This is going to be a pKb around 9. Now keep in mind, if you were in my face-to-face class, you'd have to memorize this, pKb values and pKa values. And this is an amide, okay? An amide is not basic. It doesn't have lone pairs to be basic. You know why? Folks, this is an sp2 carbon or nitrogen. It's tied up. Those electrons are tied up in resonance, and therefore they're not available to be basic. So not basic. You can't even find a pKb value. So if anything, if this gets protonated, it actually gets protonated on the hydrogen. So if you have forcing conditions, by the way, there's that plus minus, the hydrogen, they would go here. Yeah, so not basic. Rationalize why an aromatic amine is a weaker base than an alkyl amine. So this is your alkyl. Well, let's look at this. You can do lone pairs or resonance structures. So you can push those lone pairs in here. There's your negative. So when it says rationalize or explain in a situation like this, you always want to draw your lone pairs over there. You start with the negative charge and push the electrons. This should be a positive here. So now we have those lone pairs there, and that puts the negative here. And then we can draw another one where those electrons there will go here, and those go on the carbon. So when you draw these resonance structures, why would you say that this is less basic? So the nitrogen lone pairs are tied up in the aromatic ring through resonance. So they're not available to go deprotonate an acid. Rationalize why the amide is even weaker base than the aryl amine. So this is the aryl amine, and it's because those electrons are not available at all. You will not get protonation on that nitrogen of the amide. Okay, model 3 and model 4 are reactions of amines. So I also want to go over some of your slides on the reactions of amines and include some more, and then we'll go to model 3 and 4 of your POGIL. Okay, so you do have a table of the basicity of amines in your slides. I see it's number 23 of 96, and that gives you the basicity values, pKb values of those different amines, and then they also have a pKa value of the protonated amine, and you could see that you add those together and they would equal 15. So you can look at that and refer to that on your assessments. And we're going to go through the spectroscopy. I will just mention that you get a NH, like this is an NH stretch, and it's around 3,200 to 3,500 reciprocal centimeters. So it's kind of like your OH stretch, right? Except, so this is around 3,000 that you always see because you always have organic compounds, carbons. But this one here, there's two of them. So you see these two peaks, and that would be indication of a primary amine. So the primary amine would be something like this, where you would see two NH stretches. So you'd see two NH stretches, and my students used to call that the crab claw, which I thought was kind of cute. Um, so if you go on through here, you'll see that you have reactions with aldehydes and ketones. So this is a review. Here's a ketone. And if you react this with an amine, what do you get? Remember, we lost water, and you make an amine. So there's two hydrogens. There's your oxygen. And there's your amine. So you've seen that before, okay? And aldehydes, same thing. So that's a review. Okay, so there's your amine. Now, what I'm going to show you is we can make amines. So one of the things we want to do is learn how to synthesize amines. When you make an amine, you can reduce the amine with amines with lithium aluminum hydride, and that's going to make your amine. So lithium aluminum hydride would then reduce this nitrogen carbon-carbon double bond. And so what's happening here is lithium aluminum hydride delivers a hydride. And these amines are kind of like the carbonyl, where they have a polarity, and this can add here. And we don't have to go through the reaction mechanism. What you can learn is that the hydrogen will be delivered, and you can convert through reduction of lithium aluminum hydride an amine to an amine. And so if you have a primary amine and you react it with a ketone or an aldehyde, you get the amine, and then you can reduce it with lithium aluminum hydride. You'd have to have one and then two. You always have to quench it with water or acid, but this would give you a secondary amine. So this is secondary. So let's look at ways to get primary amines. So if you have a ketone or an aldehyde, and you react this with ammonia, then you can get so you lose water, oxygen, NH2, and H3. So you lose one of these hydrogens, and you have a lone pair. And then you can reduce this with lithium aluminum hydride, NH2. And that gives you a primary amine. If you wanted to make a tertiary amine, you'd have to react it with a secondary amine. So here, now how would you lose the hydrogen here? You would lose this hydrogen, and what you don't know yet is this alpha hydrogen is actually acidic, so you would lose that, and you would lose this water. And so here you make a new functional group. And this is called an N-amine. And then you can also reduce this with a lithium aluminum hydride, and this is how you would make a tertiary amine. So you can make those different amines, primary, secondary, tertiary, and this is called nucleophilic acyl substitution reaction, followed by reduction. So that's one way to synthesize the different classifications of amines. Another way is reductive amination. And I would say I probably do this once a week at Eli Lilly, because remember I told you I had to do a lot of reactions to make amines. So reductive amination, you still start with ketones or aldehydes. Okay, so you're still starting with that carbonyl, and you start with the amine. Actually, sorry. What you just did was reductive amination. So reductive amination was that. So sorry about that. Just reductant was the previous reaction. Okay, so just make a note on that. This one, you start with aldehyde ketones, and this is going to be your nucleophilic acyl substitution. And you don't start with ketones and aldehydes. You start with acid chlorides. Yeah, so you would start with acid chlorides. So here, so let's do a primary amine. And this is nucleophilic acyl substitution followed by reduction. So you're still starting with a carbonyl, but in this case, you're going, and you've seen this before, you make your tetrahedral intermediate. And now, usually you're going to have to add pyridine. So anytime you're generating HCl, which you will be from this H here and this Cl, you need to add something like pyridine. You saw this with your uracil chloride. And so you could deprotonate after. I like to deprotonate before I form my carbonyl. You'll see something different in your mechanism. And the reason why is because the protonated amine is a great leaving group, okay? So if you protonate after, then you only have one good leaving group, and that's the Cl. So I think it's a better mechanism. A lot of times mechanisms are only known so much. Okay, so this is important because we made an amide. And you'll see in the chapters on carboxylic acids, this is a way to convert an acid chloride to an amide. And then we've learned lithium aluminum hydride followed by water can reduce the amide to an amine. So this reduces that carbonyl here, and you see that you started with a primary amine and now you have a secondary amine, and that is nucleophilic acyl substitution. So you start with an acid chloride, you have to have a little bit of pyridine, and you'll make an amide, and then you can reduce that with lithium aluminum hydride. So that's tertiary. How would you make that's a secondary. How would you make a tertiary? So how would you make something like this? So you could start with this carbonyl. So make that an acid chloride here. 1, 2, 3, 4. 1, 2, 3. So let's make that one go away. Count your carbons. 1, 2, 3. 1, 2, 3. And then you can react this with a secondary amine. So you hit that with 1, and then 2 lithium aluminum hydride, and then 4 H3O plus 3. And that would give you 1, 2, 3. The nitrogen has come in here, and now you have that there, and that is a tertiary amine. So you've gone from a secondary amine to a tertiary amine. So that is nucleophilic acyl substitution. The previous name of the reaction, the previous one was reductive amination. Those are your best ways to make secondary and tertiary amines, so you can practice that. Primary amines are somewhat more difficult, and I'll go through some reactions of primary amines, and then you'll see Model 3 is, and Model 4 talks about primary amines and other reactions. Okay, so let's talk about primary amines. Let's avoid ammonia. Okay, so I don't want to give you full credit if you do those other reactions with ammonia. Yeah, you can do it, but ammonia is a pain in the butt. Okay, you're not going to choose it. You're going to have um, you're going to have to get the ammonia gas cylinder out and stuff like that. So there's other ways to make um, primary amines, and I think we have maybe 4 reactions here that will make primary amines. One of them is going to be the Gabriel synthesis, and I won't go over that here because we're going to do that in your POGL Model 3. So that's Gabriel synthesis, and that makes only primary amines. Another way is you can add sodium azide. So you've been doing this with an SN2 reaction, and then you reduce it with lithium aluminum hydride. So what does that look like? So if you have an alkyl halide, you react it with sodium azide. You have, there's your N3, and then lithium aluminum hydride, then H3O plus. That will reduce it to NH2. So you can see that that's a primary amine. Another way is to react with nitrile. So what if you did a nitrile? Then you reduce it with lithium aluminum hydride. So if you take the same reaction here and react it with sodium nitrile, you would get the nitrile is an SN2 reaction. And then you can also do lithium aluminum hydride. You can't use sodium borohydride on these, folks. It's not strong enough of a reducing agent. Then you get this compound. So what's the difference between these two? You have 3 carbons here. 1, 2, 3. Here you have 1, 2, 3, 4. 1, 2, 3, 4. So you're making a primary amine with nitrile, but you're also adding an extra carbon. And this usually trips people up, okay, when you're taking exams. You got to count your carbons. So you'll know the difference between going through a Gabriel synthesis or an azide versus a nitrile as your nucleophile. I think, okay, so before we go on to your POGL, I want to talk about arene diazonium salt reactions. So in your slides, well, let's talk about this real quick. So let's talk about your aromatic. So we've talked about this compound here, right? And so here you have an aniline, and that is electron donating group. So this is just review. So if you wanted to do nitric acid and sulfuric acid, NO2 nitronium would be your electrophile. Electron donating group would be orthopara, right? Because it has the lone pairs, and so that would be such a compound such as that. Now, what if you did we got acid chloride, and you would react that, and you put in pyridine because you're going to generate HCl. What would that give you? And that is your nucleophilic acyl substitution reaction. And now this would be still might not be so electron donating because those electrons go there. Okay, so you just got to think about that. A nitro group, how do you, a nitro group is electron withdrawing group, so that is going to be a meta director. But if you want to make it a pair director, then you can reduce it. So remember zinc, mercury, HCl, or any kind of metal, and that will reduce your nitro group to an NH2. Okay, now those are electron donating groups, and they're going to be ortho-pair directors. So let's look at a reaction scheme. So if you have toluene and you react this with sulfuric acid and nitric acid, you're adding the nitronium, and that's going to be electron donating group, so you're looking at orthopara. So let's just put it on the para. So you put your nitro group there, right? Now let's reduce that. So you can do like iron, HCl, that's in your slides, and then you treat it with some sodium hydroxide. So anytime you get the metal and HCl with a nitro group, just know that that's reducing. Sometimes there's 3 or 4 different reagents. So there's your aniline compound. Now, this is the new reaction that I want to show you. You can take an aniline and you can react this with NaNO2, 1, and then HCl. And what you get is this compound here. And this is called an arene diazonium salt. So azo means nitrogen, and there's 2 of them. So that's diazonium. It's got a positive charge, and it's a salt, and arene means it's aromatic. So these reagents here make your diazonium salt. Now, if you look through your slides on your blackboard, you will see these slides introduced starting number 74 out of 96. And it shows you how these reagents generate the diazonium salt. Don't have to know how, the mechanism to make your diazonium. I will show it here just so you can see how it's made. So actually, and it's don't do a 1-2 here. Okay, put these together and let's see how that's made. So let's do our Lewis structures. So you have nitro, NaNO2. So this is going to be well, okay. Na is a positive, so what does Na2 look like? What's your nitro look like? Right? So there's your sodium nitrate, sodium nitrite, and then you react this with HCl, and what's going to happen here is well, your slides aren't very clear, so I'm going to show you the mechanism that I would do with this. Okay, so okay, so here we have the sodium nitrite. 1, 2, 3, 4. Sodium plus, and this is your minus. Okay, so here you have your lone pair, and it's going to attack there, and this is how you get your extra nitrogen on there. So now we have N, H, we have N, you can go like that, O minus, O minus, this is a plus, nitrogen's a plus, and then water will basically take this hydrogen away, and you're going to lose, you're basically going to lose H3O plus. So you're going to, it actually does this a couple of times. Okay, so you're going to lose this and this. This is going to pick up that, and you get this intermediate. The double bond nitrogen, OH, and then you're actually going to lose even that. So this will go here, and you'll lose this, and you end up getting this nitrogen. Now let me show you about this N2. Okay, N2 is your best leaving group in the world. And why is it the best leaving group in the world? Well, 78% of our atmosphere is nitrogen. And so now once you get this molecule here, so when you add this with the sodium nitrite and HCl, you get this diazonium salt. Now what's important there is you can see that you can convert that to almost anything. So you get your diazonium salt, and you look at slide number 78 out of 96, and you can see that you can add this with just acid and heat it, and you can make a phenol compound. So you can replace that with OH. Sandmeyer. The Sandmeyer reactions use copper, so copper chloride, or copper bromide, or copper cyan. So these are your, they basically do a displacement. And so here we can replace the diazonium salt with a Cl, or a Br, or a Cn. Okay, and you can see that if you add HbF4, then it replaces it with a fluorine. Ki, potassium iodide, replaces it with an iodide. H3PO2 will replace it with just a hydrogen. And then your azo dyes, if you react this with just another aromatic compound, it will actually add the aromatic compound, and you get a azo dye. So these reactions are important in the aromatic amines. So that's kind of just bringing the aromatic amines in there. Now let's go to Model 3 and look at alkylation of amines. And we're going to look at Gabriel synthesis and the Hofmann elimination. Model 3. This is your Pogel activity 25, and this is alkylation of amines. And the first one is called exhaustive alkylation. And this is something that happens if you take an amine and you react it with an alkyl halide. And you don't even need excess, but in this case, you want to go all the way to the end. Reaction 2, you see we added another methyl. And then reaction 3, we added another methyl. And then reaction 4, we've added 4. We have 4 methyls. And there is our product. And this is showing you why you don't want to just go with an SN2 reaction. And you need these special reactions to make primary amines. So this is the Gabriel synthesis. The Gabriel synthesis is what I would prefer you to do whenever you're making primary amines. So when I see you doing the Gabriel synthesis, it will make me happy. So the first thing you're going to do is add a base. Second thing you'll do then is add your alkyl halide. And you'll see why this is more powerful, because it prevents the excessive alkylation reaction we just saw. And then the next thing you have to do is you have to add hydrazine and heat. And hydrazine will make this hydrazide, which we don't care about that, folks, okay? So that is not something we care about. So sometimes students will just draw that as their product and they get no points because you're trying to make a primary amine. And that's in the title, right? Gabriel synthesis for the primary amine. And it's only a monoalkylated primary amine is formed. Okay, I'm going to put a smiley face because that's a good thing. Now let's look at the questions. So 8. Consider the exhaustive alkylation in Model 3. For reaction 1, label the starting material as nucleophile or electrophile. So this is obviously your nucleophile, and this is your electrophile. Draw curved arrows to show electron movement. So you always go from your nucleophile to your electrophile, and then those leave. This is your SN2 reaction. And here you have to do it again. So you've added excess, so let's add another. Goes here, those leave, and then we add it again. And then we add it again. Okay. Compare the product formed in reaction 1 to the starting material. So we're going to compare this product to the starting material. Which compound would be more reactive for reaction 1? Which compound would be more reactive, the methylamine or ammonia? Well, if it's a nucleophile and you have electron donating groups, the methylamine is going to be, with electron donating groups, will be more reactive than your starting material. So circle CH3 and H2. So this increases basicity. It also increases nucleophilicity. Would you expect the reaction of ammonia to stop at the formation of a primary amine? No, because even a secondary amine has 2 electron donating groups. So this one's going to be even more reactive than your primary amine. So a secondary amine is going to be more reactive than your primary. So explain why the rate of the 4 reactions gets faster as the reaction progresses from reaction 1 to reaction 4. That's because you're adding more electron donating groups, which makes the lone pair more basic than the former. As a group, discuss why alkylating primary amines, only a little of the secondary amine is actually formed. So you would get low yield if you were trying to make a primary or secondary amine this way. And it's because of this reactivity problem. And you could just say because of exhaustive alkylation. This is why you would want to use Gabriel synthesis. So now, number 9, consider the selective alkylation in Model 3. What is the final product that results from the selective alkylation? So you see this is a primary amine. Can this final product be readily formed via the alkylation method shown in exhaustive alkylation? Nope. Question number 10. Alkylamines are generally weak acids. It takes a large amount of energy to pull off a hydrogen from an amine to form a nitrogen anion. Explain why only a weak base, only needs a weak base, is needed to pull off the anion. So actually, I'm going to tell you, you can even just buy this salt. So if you, in your synthesis reaction, want to just do the potassium thialimide, this is a stable salt that you can get. It's a nice little white solid. It's called potassium thialimide. So this is an imide when you have a nitrogen between two carbonyls. So it's a different functional group than what you've seen. Now what happens here, when you take a weak base and you take off that nitrogen, you get a nice resonance structure. And not only is this resonance structure a resonance structure, but also now you have a conjugated system where every atom is sp2. So that makes this aromatic. And so that's a huge driving force, and it becomes aromatic. So basically you just need a little weak base. You can even buy this as a potassium thialimide salt, and then you can go straight into your reaction if you would like, where you take the lone pairs here and you do your SN2 reaction. And then the next step you'd have to do, so this would be step 1, and then step 2 would be the hydrazine. And you could write into H4 is the same thing as hydrazine, and then that would give you your primary amine product. Okay, now there is a reaction that is really helpful once you do the exhaustive elimination. So once you do this exhaustive elimination, you can make alkenes, and that's what we're going to see in Model 4. So in Model 4, it's called Hofmann elimination. And so when you do exhaustive alkylation, then you can do an elimination. It's an E2 reaction, elimination, to make an alkene. So this is very useful, and it's going to be a Hofmann. So you remember we talked about Zatsev's, which is the more substituted. The Hofmann is going to be the least substituted. So how you do that here is you take your primary amine, and the first reagent you add is iodomethane, and you're going to add excessive amounts of that because you do want exhaustive alkylation. That's the first thing you want with step number 1. And then step number 2, you're going to react with silver oxide and a little bit of water. This is going to generate an OH minus, okay? So we'll talk about that. And then the third thing you want to do is just heat. And your product then is going to be, how many carbons you got? 1, 2, this is 1, 2, 3, 4. So you can say butylamine. And now you're going to have this compound here, which is an alkene. So question number 11. Step 1 of the Hofmann elimination is called exhaustive methylation, which occurs in excess methyl iodide. Draw the products of the over alkylation. So a lot of times I do want to see you draw your products for each step, reaction step. Here, this would be replace every one of these hydrogens with a methyl, and there you have your product for 1. And you don't have to go through that whole exhaustive methylation, each reaction step. You can just draw this. All right. Step 2, so B, involves exchanging an anion from iodide to the OH minus. Draw the product. So silver, you can write this, silver loves iodide. And so if you throw in some silver oxide, then the silver iodide is going to complex each other and it's going to precipitate out. Remember precipitation reactions? So what happens now is this reagent will replace the iodide with just an OH minus. And we know that that's a strong base, right? So here, this is an alpha. This is your alpha. And when we're doing E2, we're doing Hofmann eliminations. These are your hydrogens here. So now, step 3, or C, step 3 is a beta elimination reaction, which occurs upon heating. And so what happens is these electrons here will come and take your beta hydrogen. Those electrons go, and this is a great leaving group. So this is going to leave to form trimethylamine, and now you have your alkene and water. So this is your OH, hydrogen went there, and you still have this. So this is your alkene. And it's driven by the basic counter ion. Label the alpha and beta positions. So we just did that. Draw the product in step 2 in a Newman projection along the alpha-beta bond. For beta elimination, what relationship is needed for the leaving group and the beta hydrogen? So let's draw our Newman projection. So we just draw our framework here, and then we draw our back carbon here. And we know, so this is, where's our leading group? So this is our leading group. So we're going to put our leaving group here, CH3, and we know we need to have it 180 degrees from our back carbon hydrogen. So we know that this hydrogen, our beta hydrogen, needs to be 180 degrees from the leaving group. So this is your alpha. And what else isn't showing there is the 2 hydrogens, so you can put those there. And then you can go to your beta here, and you have 1 hydrogen, and then you have CH2, CH3, which is this group here. So that is your Newman projection, and this is your leaving group, and this is your beta hydrogen. So the OH will take that, those electrons go there, and there's your leaving group to give you your 180 degree anti-periplanar structure that must occur for an E2 reaction. Okay, let's omit question 12, number 12, so that's pretty much page 303. And just note that you're going to get your Hofmann elimination. Now let's look at a reaction that would make a difference here. So what if you had this starting material here, okay, and you added excess methylamine, then you added silver oxide and water, and then you added heat. What would your product be? So in this case, this would be your Hofmann. Okay, so that would be your Hofmann product. The Zaitsev product would be, so here's your alpha. So this is going to be in CH3, 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 plus the iodide is going to get replaced with the OH. And then upon heat, you have this beta, and then you have these betas. Hydrogen, and you choose the one that gives you the Hofmann product over the Zaitsevs. Let's look at your additional problems. You need to draw the conjugate acid from each amine base, so I expect you to draw your conjugate acid, and for each pair of amines, so you'll have 2 pairs of amines, which amine is the most basic, and explain. So you'll need to draw your conjugate acids for each one of these. You can use your pKb values and you can look those up, but I need you to do an explanation. And so some explanations are aliphatic versus aromatic, um, or aromatic, or aliphatic versus aryl. And so you can compare those two and have an explanation. So I'm looking for an explanation. 14, you want to rank those basicities. I'm going to go ahead and tell you there's an amide, and you need to address it as an amide. It is not going to be basic, and I don't know why you have two amides there. So anyway, I don't even really like that question. So, but you should be able to pick between an amide and an aliphatic amine. 15, you're actually going to do acid-base reactions. So I would encourage you to do acid-base reactions in terms of pKa values. So why don't you do like how we've done acid-base reactions, where you have to draw your products, you label acid-base, conjugate bases, you assign pKa values to both acid and conjugate acid, and then do the equilibrium arrow. 16, you're doing the reactions that you reviewed in models 3 and 4.